In this lecture, we will explore the natural response of an RC circuit. Capacitor is said to exhibit a natural response when the stored energy within it is abruptly released. In such a case, the resulting response is fully dictated by the capacitor as there is no external independent source involved in the circuit under test. The natural response of an RC circuit can be best described using the illustrated figure. We will assume that an independent voltage source, Vg, has been connected with the capacitor for a long time. This means that all voltages and currents have reached their final constant steady-state values. Therefore, the capacitor behaves as an open circuit, as it has already been charged to supply voltage Vg. This provides us with an initial condition where the capacitor voltage at time t is equal to 0 is Vg. Now we will move the switch from position A to position B at time t is equal to 0, disconnecting the voltage supply from the capacitor. The new circuit after the switch is moved to position B can be drawn as shown. As there is no independent source left in the circuit response will be fully dictated by the capacitor. Therefore, this response can be classified as a natural response. We know that as the capacitor gets disconnected from the voltage source, its voltage cannot reduce to 0 immediately. The energy stored in the capacitor will be slowly released, consequently preventing an abrupt change in capacitor voltage. At this time, the expression for the circuit using Kirchhoff's currents law can be written as. After rearranging, the equation can be written as. We aim to find the capacitor voltage as a function of time after the switch has been moved to position B at time t is equal to 0. By integrating both sides, where V0 is the initial capacitor voltage at time t is equal to 0 and solving for the integral, we get. Based on the definition of natural logarithm, the logarithmic term can be converted into an exponential form as shown. The resulting expression gives the capacitor voltage at any time greater than 0. We can analyze the equation by equating time value of 0 and infinity. At t is equal to 0, the exponential term is 1, resulting in a capacitor voltage of V0 or Vg at time t is equal to 0. On the other hand, as t approaches to infinity, the exponential term goes to 0, meaning that after a very long time, all the voltage across the capacitor will eventually reduce to 0. This can be represented graphically, showing the capacitor voltage starting from an initial value of Vg and gradually decreasing to 0 over time. Just like in the derivation of natural response of RL circuits, we can define time constant for the capacitor natural response. The time constant for capacitor will be given as τ is equal to RC. A practical example of natural response of an RC circuit can be seen when we power off a small LED light circuit in a remote controlled or other battery operated device. When the device is turned off, the capacitor that was supplying voltage to the LED will discharge through the internal resistance of the circuit, causing the LED to gradually dim. This concludes our discussion on the natural response of RC circuits. In the next video, we will take this further and discuss about the step response of RL circuits. So until next time, stay tuned.